first problem, let's take the 2 times the sine of x minus 1, set that equal to 0. If you consider strategies that you've used in the past to solve any equation, normally if you've got variables involved, you try to get that variable by itself. So here I have a variable expression, sine of x. If I could get that much by itself, maybe I could start using some of this inverse stuff from last time. So solving for the sine of x, I'm going to add 1 over. If I add 1 over, I'm going to divide by 2 after that, right? I divide by 2 to isolate this sine of x. I've got the sine of x equals 1/2. Now I'm still trying to get x by itself. So to get x by itself, since I've got the trig function attached, to drop that trig function, we apply the inverse of that trig function to the other side. And hey, what do you know? We're back where we were the last time. If I need to apply the inverse sine to 1/2, understanding that sine is opposite over hypotenuse, I can set up my right triangle over here if I need to draw it out, or I can just go to the special right triangles that I've got listed probably somewhere in my notes. But if I set this up, letting this angle be my x that I'm looking for, opposite is 1, hypotenuse is 2. Already kind of gave away what the answer is going to be. But what would x have to be as a degree measure to start? It's going to be 30 degrees, right? So if it's going to be 30 degrees for the degree measure, the radian measure, since we have to have an answer on this interval 0 to 2 pi, that's going to be pi over 6. Now, just like we did in the last section, got to go back and consult the kind of value that we're plugging in here. You know, is it positive? Is it negative? In this case, it's positive. So since that's positive, we're talking about sine. We got the first quadrant covered with the positive values because we got pi over 6 as an answer. But now I need my answers from the second quadrant since sine is also positive there. So the pi over 6 value from the second quadrant would be what? 5 pi over 6. Should we memorize the unit circle?
Again?
Probably wouldn't be a bad idea to go back and do that. Otherwise, we got to do some counting to find these values.
Yeah.
So you have pi over 6 and 5 pi over 6. That would be my 2 solutions to this equation. All right, for this second one, we'll start with a scenario again where everything equals 0. This time we'll use cosine, so it'll be 2 cosine squared of x minus 7 cosine of x plus 3 equals 0. Now if you go back and consider what we just did on the first problem, we try to isolate the variable expression. Here we've got a couple of variable expressions that have some cosines involved. If you look at the form that you have here and try to think back to other algebra problems that may have been similar to this form, you'll notice that I've got something over here that's squared, and then I've got that same idea here. So I'm kind of throwing a variable in here just to make that comparison. Because off to the side, if it's easier for me to do this, I could rewrite this as 2a squared minus 7a plus 3 equals 0, as long as I'm letting that cosine be the a variable, right? If you look at this equation, this should be something you know how to solve. So let's solve this one instead. If I solve this one instead, I try to factor it. As I try to factor it, I've got a 2a squared, so it's got to be 2a and a, right? I've got a 3, so it's got to be a 1 and a 3, or a 3 and a 1. Makes sense to be 1 and 3. And if I'm going to FOIL this all out to get the negative 7a, those would have to be negatives, right? So I factor to 2a minus 1 and a minus 3, and then I split up the factors, setting each of those equal to 0. Solving over here, a obviously will be 3. Solving over here, you've got 2a equals 1, so a would have to be 1/2. And if a represented cosine in the first place, now that I've done all the dirty work off to the side to solve that original form, I could take these pieces and reintroduce the cosine to those parts. In other words, I could write cosine of x equals 1/2, and cosine of x equals 3. So that's kind of a creative way to get around just working directly with the trig stuff and using some old-fashioned algebra.
But the square goes away when you solve it like algebra.
Yes. So now if I'm solving for x for either of these equations, I'm applying the inverse, which allows me to drop these cosines out. So x is going to equal inverse cosine over here of 1/2, and x over here is going to equal inverse cosine of 3. All right, if I consider this first equation, this first inverse, if I draw out my triangle to try to determine what x is, here's my x. For cosine, we're talking adjacent value over hypotenuse, right? So adjacent is 1, hypotenuse is 2. What would this angle measure have to be to make that work? Okay, it's going to have to be 60. So since it's 60 and we're talking radian measures, pi over 3 would be the answer, at least one of the answers, because we know cosine is positive. Now the other quadrant where cosine is positive is where? Fourth quadrant. So pi over 3 has built the foundation for our answers here. We know the fourth quadrant also includes one of those answers. So what's the pi over 3 value in the fourth quadrant? The only pi over 3 value in the fourth quadrant is 5 pi over 3. So two answers for x. We've got pi over 3 and 5 pi over 3. But we still need to consider this other guy. All right, for this other guy, if we start to draw things out, trying to figure out what x is. Taking the inverse cosine of 3, that would be 3 over 1. So adjacent would be 3, hypotenuse would be 1. No such triangle is going to work, right? If you think back to what we were talking about earlier in the class with those questions we had in 7.4, this would be an example where we're not going to get an answer. It's not going to exist. So do we write does not exist? Don't really need to write does not exist for this side. I could just kind of take it out of there. Because after all, we do have answers that exist. Those answers are right here. Now let's take 3 sine of x, set that equal to 2 cosine squared of x. Got two different functions working within this equation. You go back and you look at how the other ones were set up. For the other ones, they were all equal to 0 in the first place, right? So maybe that's a strategy to use here. Let's go ahead and set these all equal to 0. To do that, I might take this 2 cosine squared of x, subtract it over. If I subtract that over, I've got 3 sine of x minus 2 cosine squared of x set equal to 0. Now, if you look at what we have here, we have a problem because you do have 2 trig functions in one. This is where you try to reduce it to one kind of function, and you introduce identities. You remember things like cosine squared of x being equal to something in terms of sine. Right? Cosine squared of x is the same as 1 minus sine squared of x, right? If I plug that in, I'd have 3 sine of x minus 2, replace cosine squared with 1 minus sine squared. All of that we set equal to 0. So get everything to one side. If you got 2 functions you're working with, try to at least replace one of them using an identity. Now we're just working in terms of sign on this problem. So solving this equation, following the algebra rules you always have, you distribute. Right, once we have parentheses in the equation, we want to get rid of the parentheses. So distribute the negative 2 through. You've got 3 sine of x minus 2 plus 2 sine squared of x. All of that equals 0. Always trying to take these equations and turn them into something that I'm already familiar with in terms of solving. I've got kind of a messed up order here, but if I rewrite it with the squared term first, and then the non-squared term second, and the constant last, hey, what do you know? We're back at the same kind of equation as we had on the previous problem. Or if that little trick worked, and you take this idea here, introduce a variable for sine, and off to the side say 2a squared plus 3a minus 2 equals 0, we could try to solve that equation. So create my little thought bubble up here. Trying to factor this one out to solve. Well, 2a squared, so it's 2a times a. This time we've got a 2, so it's got to be 1 times 2 or 2 times 1. Let's try the 1 times 2 combination. If we let this be positive and this be negative, that should give us that 3a when we FOIL things out, right? So now you've got your 2 factors. Set each factor equal to 0. Solve for each a. Over here, a would equal negative 2. Over here, you got 2a equals 1. Divide by 2, a is 1/2. Once you got your a's, reintroduce the original trig function, which was sine. So sine of x equals 1/2. And sine of x equals negative 2. To drop out the signs, we apply the inverse to both sides. So here we've got the inverse sine of 1/2. Over here we've got the inverse sine of negative 2. Okay, so over here, yeah, if you've been paying attention, we know this one's not going to work. Not going to get an answer out of that. But for this other x, you've got your opposite, you've got your hypotenuse. Everything's positive for the sine, so if I bring that guy over here, draw out that triangle, if it helps. There's my x, opposite 1, hypotenuse 2. What does x have to be? X has to be 60? Should be 30, right? 30 degrees, and if it's 30 degrees, we're talking pi over 6. Once again, sine is positive over here with the 1/2. So since it's positive with the 1/2, second quadrant, we need the pi over 6 value as well that works. That would be 5 pi over 6. So even though one part of this did not exist, we still get answers that do exist. Those answers are pi over 6 and 5 pi over 6. All right, I got one last one here I want to do with you. And it's probably worth our time to maybe look at something in the packet too. For this last one, let's look at tangent. In fact, let's square tangent. And let's spice up the argument a little bit. Instead of having an x in here, let's have a 2x. Tangent squared of 2x minus 3 equals 0. This one should appear a little less intimidating than the previous two. Right? We don't have the fancy factored form that we got to go for. We've just got the single trig function that we need to isolate. So let's do that. If we isolate this, got tangent squared of 2x. Go ahead and add the 3 over. Now trying to get at least the tangent of 2x by itself. You want to get rid of this squared part, right? So to do that, you got to take the square root of each side. But if you're going to take the square root of each side and you're solving an equation, you got to have a plus or minus in there. Got a lot happening at that step. But remember, it's the same rule we've always followed when you apply a square root to each side. Okay, if you want to eliminate tangent, to try to squeeze this 2x out of all of it, you take the inverse tangent of each side. So I apply the inverse tangent to the plus or minus root 3. And don't worry about this 2 right now. Yeah, I know at some point we need to divide that over. But we need to try to simplify how much we're doing at one time. Let's just focus in on the inverse. That's what we've done on all the other problems anyway. Try to figure out that much of it. If we're going to focus in on the inverse and we're talking tangent, as a ratio, this root 3 would be over 1, right? And as a ratio, talking in terms of tangent, we're looking at opposite and we're looking at adjacent. So if I draw out a triangle to try to match this up, if I stay consistent here, let my little variable be x. In fact, we could argue that's a 2x right now. Opposite, we'll let that be root 3. Adjacent is 1. You know, if we're thinking about our special right triangles here, hypotenuse would be 2, meaning x is what? Well, actually, it would have to be 60, right? This is going to work. So we're solving for 2x. And the way we're solving for 2x is we're applying the inverse. We've just found that this angle has to be 60 degrees, so that's pi over 3. And we consider the signs on this value we're plugging into the inverse tangent. It's positive and negative, right? Normally it's just been one sign or the other, and we end up with 2 answers because we can only work with 2 quadrants. How many quadrants are we going to work with here? All 4. Right? All 4, because we've got tangent being positive, which is true in 2 quadrants, and we got tangent being negative, which is true in 2 quadrants. So we go all the way around. If we're going all the way around, pi over 3 takes care of the first quadrant. The pi over 3 value in the second quadrant that we would need would be 2 pi over 3. Now moving down to the third, the pi over 3 value we would need 4 pi over 3. And then the fourth quadrant, 5 pi over 3. And I know what you're thinking at this point. It's like, wow, this is a lot of fun because we got a plus or minus, so we got to do more stuff. But there's more. There's more because we've got a 2 right here. And maybe you're thinking, well, all I got to do is divide the 2 over. At some point we do, but what that 2 means is we get to take another trip around the unit circle. If it's just 1x, you go 1 time around. If it's 2x, you go 2 times around. If it's 3x, you go 3 times around. So on this one, we take another trip. When we take another trip, we're now back to the first quadrant again, and the pi over 3 value in the first quadrant. On the second trip around, okay, if we're counting here, let's think about this. We were at 5 pi over 3. 6 pi over 3 would be 2 pi, so that's not it. 7 pi over 3. If we keep counting, second quadrant would be 8 pi over 3. And we like this counting stuff because now we're at 9 pi over 3, but wait, that reduces. Right, that's 3 pi. So the next one would have to be 10 pi over 3, and now I just can't stop counting, but I probably should after this next one because this would be the fourth quadrant, right? This would be 11 pi over 3. So here's the first go-around, 4 answers. Here's the second go-around, 4 answers. Finally, we are able to isolate the x by dividing 2 over. And when you divide 2 over to a bunch of fractions, it's the same thing as multiplying by 1/2, just double all your denominators. You got pi over 6, you've got 2 pi over 6, right? Reduce as you go. 2 pi over 6 would be pi over 3. You got 4 pi over 6. Reduce as you go, you got 2 pi over 3. You got 5 pi over 6. You got 7 pi over 6. You got 8 pi over 6 reduces to 4 pi over 3. You got 10 pi over 6, which is 5 pi over 3. And you got 11 pi over 6. Notice how all of your answers now fall between 0 and 2 pi. It's flippin' magic.